Hi everyone, this is Hao-Yin from Georgia Tech. Today it's my pleasure to share with you our work in Interspeech 2023 Neural Model Reprogramming with Similarity-Based Mapping for Low-Resource Spoken Command Recognition. And before I start, I would like to credit this work to all the co-authors listed here. So let's get started. So for the motivations of this work, as we know, building a high-performance speech recognition system often requires preparing a large amount of label training data, which is not always realizable or possible in real-world scenario. And therefore, a low-resource training scenario is more favorable for a broader human speech processing tasks. It is also gaining much attention as NIST has been hosting an open ASR challenges for low-resource languages for these past few years. However, there are some challenges that lie in low-resource training. First of all, it is obvious that it would be hard to train from scratch with deep neural networks when you only have limited numbers of training data. And a common way to deal with low-resource training is through fine-tuning. However, we also noticed that fine-tuning a large pre-trained model with only a few target domain samples is a challenging task due to obviously lack of data points, but also domain mismatch where the target domain is distinct from the source domain. And a bit of background introduction to how we evolved from frozen model adaptation to neural model reprogramming. Say we have a pre-trained models trained on its own data and label pairs. We use the universal approximation theorem, which tells us that if we define a loss functions, it can upper bound the test error in the above equations, which actually consists of two terms, an approximation error and an estimation error. And in essence, these two terms correspond to the frozen pre-trained model and the model adaptation, respectively. So what actually is neural model reprogramming and how we could relate it to speech? So in essence, neural model reprogramming is the combination of trainable perturbations and frozen pre-trained model, which directly corresponds to the above theorem. So bearing the above motivations and background in mind, in this work, we propose a neural model, or we could call it adversarial reprogramming, and a similarity-based label mapping technique in order to tackle the above mentioned low resource challenges. So to be more specific, we focus on low resource spoken command recognition tasks using minimal training data. So spoken command recognition is to identify a target command out of a set of predefined candidates based on the input utterance. So say we have an utterance says the word yes, we would like the model to recognize it as yes. And overall, we achieved new state-of-the-art on the Arabic dataset, as well as the Lithuanian dataset, even under the most challenging few-shot scenarios. So how do we apply adversarial reprogramming to spoken command recognition? Here we show the framework of our overall system. It is quite simple and straightforward. It consists of a reprogram layer, a pre-trained acoustic model, and finally a label mapping process. So what is a reprogram layer? It aims to transform the input signals to reduce the distance of target and source distributions by adding a trainable noise or trainable perturbation, as we mentioned before. The overall equation is also quite simple, as shown here, where theta is the trainable noise. And note that in the plot here, we don't actually make the Lithuanian command no to sound like the English command no. We just want the pre-trained model to recognize it as English no after the transformations. So after the transformation, we feed xt prime here, which is the reprogrammed signals, to the pre-trained acoustic model, and it will produce us with the source class probabilities. And in this work, we pre-train our acoustic models on a large-scale benchmark dataset, Google Speech Command. And finally, we need a label mapping process to map the probabilities of the source commands to that of the target command. But how do we actually perform a label mapping? Say we have a target domain spoken command. Let's hear the examples first. This is the original signal command 1 in Lithuanian.
Vienas.
This is for dysarthric Mandarin, also the command one. And here is the reprogram signals.
Yeah.
And for Mandarin. So here we could hear that there are some background noises in the reprogram signals, and that is actually our trainable noise aiming to transform the original signal. So how do we actually map the source class probabilities to that of the target class probabilities? Private literatures have shown that random mapping can be a way. Random mapping includes one-to-one mapping, where we randomly select one source class and map it to one target class. Or we can do many-to-one mapping, where several source classes probabilities sums up to a particular target class. However, although this method can provide a solution to the mismatch of number of source and target classes, it does not consider the relationship of data in source and target domains. And therefore, in order to address the above mentioned issues, we proposed similarity mapping. And here is a random many-to-one mapping just for comparison. So the goal of similarity-based mapping is to find the optimal many-to-one mapping technique that can leverage the structural relationships of each label classes in source and target domains. So here we show the average representations of several source target pairs based on the PCA plots. And we can see that there exists some relationship between each source and target pairs. So empirically, we use the average representations produced by the pre-trained acoustic model and compute the similarity of each label based on cosine similarity. So based on the cosine similarity results, we assign a few source label probabilities to each target label that are closer together. And we can see that the results make much more sense, as the acoustic representation of the word no and nine is probably more similar to Lithuanian command no, and therefore we map those two source class probabilities to the target command no. And as compared with the random many-to-one mapping, where it fails to do so during mapping, as it maps no and stop to the Lithuanian command no. And here we show the semantic illustrations of all the setups and models we have in this work. So first of all, the baseline system, it's really straightforward. We train from scratch with all the languages and all the data we have. And then the transfer learning systems, where we've pre-trained our models on Google Speech Command, as we mentioned above. And then we fine-tune the whole models, pre-trained acoustic models with the data we have. And then it comes to our proposed adversarial reprogramming systems, where we use an input trainable noise combined with the frozen pre-trained acoustic models, as we mentioned in the background, and also the adversarial reprogramming page. And we also further combine adversarial reprogramming and transfer learning to see whether these two techniques and methods are complementary and can give us better results. So now we introduce some of the low resource speech command recognition datasets we use in this work. First of all, the Lithuanian dataset, which consists of 15 target commands with around 20 samples for each command. And we further consider a more extreme cases where we randomly select smaller subset from the full dataset with only 3 samples and 10 samples per each command. And secondly, the dysarthric Mandarin speech command recognition dataset, we select 13 short commands that's around 1 second to form our training and testing dataset. And for each target commands, we have around 20 samples for each command. And now we show the results of all the systems we listed above for comparisons. And note that all the results here are average of 10 experiments. So first of all, we can see from both tables the effectiveness of our proposed method as adversarial reprogramming combined with transfer learning consistently achieves the best overall performance among the 5 systems, outperforming traditional method, dynamic time warping here, baseline train from scratch, and also transfer learning alone. Secondly, we demonstrate the data efficiency of our proposed system, as we can see from table 1, that the relative improvement becomes better and better and more significant as we consider a more challenging future scenarios, especially when we only have 3 samples per each command. We observe a 72.8% relative improvement from the baseline systems. And finally, our proposed adversarial reprogramming can achieve better performance stability when combined with transfer learning technique, and it can be observed based on the low standard deviation values as we show in the tables. Furthermore, a new state of the art has been achieved with our proposed methods, and here we show the results as compared to the state of the art systems. So for the Arabic dataset, a bit of introductions. It consists of 16 commands, including 6 control words and 10 digits. And for each command, there are around 100 training samples. So for the Arabic speech command dataset, we actually observe that adversarial reprogramming combined with transfer learning can achieve the highest accuracy of 98.9%, which outperforms the LSTM state of the art at the time. And it is also worth noting that adversarial reprogramming alone can achieve a relative competitive results with much fewer parameters. But of course, when combining with transfer learning, it yields an even better performance. And we also report our batch 1 accuracy of the Lithuanian speech command dataset as compared of the state of the art system. We show that adversarial reprogramming with a much smaller acoustic model can outperform web-to-vec, which to our best knowledge is the state of the art when we conducted the experiments. And now we also conducted an ablation study where we demonstrate the results when combining adversarial reprogramming with data augmentation technique, which is also a commonly used technique under low resource scenarios. And to be more specific, we use spec augment as our augmentation method. So from the table, we can easily observe that data augmentation can improve and stabilize the performance of adversarial reprogramming by a large margin. And so far, we have shown that adversarial reprogramming can be successfully combined with transfer learning and data augmentation, and the improvements were complementary. So this also tells us that the proposed adversarial reprogramming has great flexibility to combine with other advanced training techniques commonly adopted in neural model training lower resource. Finally, that brings us to the last part. And for the conclusions, this work, we introduce an adversarial reprogramming approach to establish a speech command recognition system with a very limited amount of training data. And also experimental evidence shows that the proposed system can consistently achieve superior performance as compared with state-of-the-art speech command recognition methods on the Lithuanian and Arabic speech command datasets. Also for future work, it is obviously shown that it is entirely feasible to expand our effort towards reprogramming of different speech models for challenging low resource speech tasks, such as speech synthesis. Also, important part of reprogramming is that we could leverage the recently emerged and advanced speech foundation models. And we would like to motivate the community into improving accuracy even further through the reprogramming techniques we proposed. And here are some references we mentioned in this presentation and also in our work, in our paper. And that brings us to the end. We would like to mention that we open sourced all the codes and hyperparameters for reproductions. So feel very welcome to try our implementations, as we are excited to motivate more and more research ideas using this kind of reprogram techniques. And I would also like to credit this work again to all the co-workers listed in the first page, and my PhD advisor, Professor Qinghui Li, for providing valuable opinions and perspectives during the discussions. And before I finish, I would like to thank you all for your attention and interest in crediting our work as one of the candidates for Best Student Papers. I look forward to Interspeech 2023, and I hope to see you all there. Thank you.